Black holes have long been one of the most enigmatic and mind-bending phenomena in the universe. These regions in space are so dense that not even light can escape their gravitational pull. For decades, scientists, including theoretical physicists like Michio Kaku, have theorized about what could possibly lie inside these mysterious cosmic objects. Kaku, a prominent figure in the world of theoretical physics, is known for his engaging explanations of complex concepts. In recent years, he has made bold statements about breakthroughs in understanding black holes and their internal structure. In this article, we explore what black holes are, the various theories proposed about their interiors, and Kaku's perspective on what might finally be known about them. The nature of black holes. Black holes are formed when massive stars collapse under the force of their own gravity at the end of their life cycle. As they collapse, all of their mass is concentrated into an infinitely dense point known as a singularity. Surrounding this singularity is the event horizon, the boundary beyond which nothing can return. The idea that something can exist where not even light can escape has fascinated and perplexed scientists for decades. The idea of black holes has been around since the late 18th century, but it wasn't until Albert Einstein's theory of general relativity in the early 20th century that the concept gained scientific credibility. In Einstein's framework, massive objects bend spacetime, and black holes are extreme examples of this curvature. Anything that crosses the event horizon of a black hole gets stretched and ultimately pulled into the singularity. However, despite understanding the general mechanics of black holes, their inner workings remain a mystery. For a long time, scientists thought the singularity was a point where the laws of physics as we know them break down, leading to questions about what lies beyond that veil. Classical theories about black holes. The standard model of black holes is based on Einstein's equations of general relativity, and for many years, physicists accepted that once you cross the event horizon, all paths lead to the singularity, where matter is compressed into an infinitely small point. Time and space as we understand them cease to exist. However, this classical view of black holes raises paradoxes. For one, the information paradox questions whether information that falls into a black hole is lost forever or somehow conserved. This issue contradicts the principles of quantum mechanics, which states that information cannot be destroyed. The event horizon also marks a point of no return, but what happens inside has always been speculative. For many years, the idea of a singularity was accepted, though troubling to physicists because singularities imply infinite density and zero volume, concepts that are physically challenging and mathematically problematic. Quantum mechanics and the information paradox. One of the biggest puzzles in theoretical physics is the conflict between general relativity and quantum mechanics. Black holes sit at the heart of this debate. According to general relativity, the information that enters a black hole is lost forever when it reaches the singularity. However, quantum mechanics insists that information cannot be destroyed. This paradox led to some of the most intense debates in physics for decades. Hawking radiation, a theory proposed by Stephen Hawking in 1974, suggested that black holes slowly evaporate over time by emitting radiation. As the black hole evaporates, it loses mass and eventually could disappear altogether. However, the radiation emitted carries no information about the matter that has fallen into the black hole, deepening the mystery of the information paradox. Recent advances in quantum theory have led to suggestions that black holes may not be the information-destroying entities they were once thought to be. Some scientists now believe that the information may be preserved in a scrambled form in the black hole's event horizon or even in the particles that escape as Hawking radiation. However, this issue remains unresolved, and new theories are continuously being developed to explain the inner workings of black holes. Michio Kaku's insights on black holes. Michio Kaku is known for his work on string theory, a framework that attempts to unify quantum mechanics and general relativity. Kaku believes that string theory may provide a way to solve the mysteries of black holes, particularly the problem of the singularity. In several interviews and public discussions, Kaku has suggested that black holes might not contain a singularity at all. Instead, they may be gateways or portals to another universe or dimension. In Kaku's view, the singularity at the center of a black hole could be replaced by a wormhole, a theoretical passage through space-time that connects different regions of the universe or even different universes entirely. If this is true, then black holes could be far more than just cosmic dead ends. They could be paths to alternate realities. Another important point Kaku makes is that our current understanding of black holes is limited by our inability to merge general relativity with quantum mechanics. String theory, which posits that the fundamental building blocks of the universe are not particles but tiny vibrating strings of energy, may offer a way to understand what happens inside black holes. Kaku suggests that string theory might prevent the formation of a singularity by creating a new kind of geometry inside the black hole. In his popular writings and talks, Kaku often emphasizes that black holes might not be the ultimate cosmic prisons we once thought. Instead, they could play a role in the formation of new universes. According to this theory, when a black hole forms, it creates a singularity, but instead of collapsing into infinite density, it could act as a big bang for a new universe. This idea ties into the concept of the multiverse, which suggests that our universe is just one of many in a larger cosmic landscape. Breakthroughs in black hole research. In recent years, there have been several exciting breakthroughs in black hole research. One of the most significant was the first-ever image of a black hole, captured by the Event Horizon Telescope in 2019. This image, showing the shadow of a black hole in the center of galaxy M87, provided direct evidence of the existence of event horizons and offered new insights into the behavior of black holes. Another breakthrough came in the realm of gravitational waves. In 2015, scientists detected gravitational waves for the first time, confirming a key prediction of Einstein's theory of general relativity. These waves were generated by the collision of two black holes, providing new information about how black holes interact and merge. Since then, multiple detections of gravitational waves have allowed scientists to study black holes in ways that were previously impossible. In addition to these observational breakthroughs, theoretical work continues to push the boundaries of what we know about black holes. Advances in quantum theory, particularly in understanding how information may be preserved in black holes, are helping to resolve the information paradox. Some physicists now believe that the interior of a black hole could be more like a fuzzy region where quantum effects dominate, rather than a singular point of infinite density. What's next for black hole research? Michio Kaku's enthusiasm for black hole research reflects the growing excitement in the scientific community about what these cosmic objects can teach us about the universe. While we are still far from fully understanding what lies inside a black hole, recent advancements in both observational astronomy and theoretical physics have brought us closer than ever to unlocking their secrets. The next frontier in black hole research will likely involve even more detailed observations of event horizons and gravitational waves. As technology improves, scientists may be able to probe closer to the event horizon, providing new insights into the behavior of matter and energy in these extreme environments. In parallel, theoretical physicists like Kaku continue to explore the implications of string theory, quantum mechanics, and general relativity in the context of black holes. The ultimate goal is to develop a unified theory of quantum gravity that can explain what happens at the heart of a black hole, possibly revealing new dimensions of reality in the process. Conclusion: black holes are among the most fascinating and mysterious objects in the universe. For decades, scientists have sought to understand what lies inside these cosmic behemoths, but many questions remain. Michio Kaku's contributions to the field, particularly his work on string theory and the possibility of black holes being gateways to other dimensions, have sparked new interest in solving these mysteries. While we may not yet have all the answers, recent breakthroughs in both theory and observation suggest that we are on the cusp of a new era of black hole research. Whether black holes contain singularities, wormholes, or something entirely unexpected, one thing is clear: these mysterious objects hold the key to understanding the deepest laws of physics and the true nature of our universe.